Hello class, in this video I'll be describing some characteristics of relative extrema and provide the steps needed to locate and test for relative extrema. Let's begin. So in this diagram, we will start by claiming that AB is the location of a relative maximum. And in this diagram, that's true. Notice that there are two tangent lines. One that I'll highlight in green and one that I'll highlight in blue. And what is special about those two tangent lines? Well, both of them are horizontal. And what does that mean? Well, starting with the tangent line in blue, since the tangent line is horizontal, the slope of the tangent line is 0, so the partial derivative with respect to x at AB is going to equal 0. And how do I know it's the partial derivative with respect to x? Well, the tangent line that's highlighted in blue runs parallel to the x-axis. Onto the tangent line highlighted in green. Since the tangent line is also horizontal, the slope of that tangent line is 0, and we can conclude that the partial derivative with respect to y at AB is equal to 0. And why do I know it's the partial derivative with respect to y? Well, it's because the tangent line highlighted in green runs parallel to the y-axis. So in this diagram, we started with the fact that AB is the location of a relative maximum and concluded that both partial derivatives were equal to 0 at the same time. So what I'm going to do is I'm going to show you a statement that's true all the time. And here it is. If there is a relative maximum or minimum at the point A comma B, then both partial derivatives at AB will equal 0, provided that both partial derivatives exist. Okay. So that statement is true all the time. But what happens if we started with both partial derivatives equal to 0 first and tried to conclude that there was a relative maximum or relative minimum? Well, we can't do that. Actually, in fact, the converse of this statement is not always true. All right, so what do I mean by the converse? All right, so I'm going to write down the converse now, and the converse is going to start with if both partial derivatives at the point AB equal 0, then there is a relative minimum or maximum at A comma B. Okay, so as I stated, the converse is not always true. So if we're given that both partial derivatives are equal to 0, we cannot conclude that there's a relative minimum or maximum there without further testing. And here's what I mean. We will take a look at this example here. And I'm going to put a point or a red dot at the origin. So there's what's called a saddle point at the origin. So there is a saddle point at the origin. And what does it mean for there to be a saddle point at the origin? Well, that means both the partial derivative with respect to x and the partial derivative with respect to y equals 0, however, there is no relative minimum or maximum at the origin. Okay. So both partial derivatives at the origin equal 0. So if I were to draw a tangent line parallel to the y-axis and a tangent line parallel to the x-axis, the slopes of those tangent lines will equal 0, so the partial derivatives at the origin will also equal 0. But if we take a closer look at what is happening at the origin here, if I were to trace some output values that were parallel to the y-axis, notice those output values are smaller than the output value at the origin. If I were to trace output values that were parallel to the x-axis, notice those output values are larger than the output value at the origin. So we can't make a conclusion as to whether the origin is a local max or a local min. Hence, we're going to call it a saddle point. So how can we test whether a coordinate is either a relative max, a relative min, or a saddle point? Well, we're going to start by finding the location of the extrema, and that is where you're going to find the coordinate where both partial derivatives are equal to 0. And once you've done that, once you've found out where both partial derivatives are equal to 0, you can use what's called the discriminant to determine if that's the location of a minimum, maximum, or saddle point. And notice that the discriminant requires second-order partial derivatives. And there are 4 outcomes. Outcome A. F of AB is a relative maximum if the discriminant is greater than 0 and the second-order partial derivative at AB is less than 0. F of AB is a relative minimum if the discriminant is greater than 0 and the second-order partial derivative at AB is greater than 0. F of AB is a saddle point, which is neither a maximum or a minimum, if the discriminant is less than 0, and if the discriminant is equal to 0, the test gives no information. Now, this test can be used on your exam. It doesn't have to be memorized, but please make sure you understand how this test works.